Welcome to video 4 and the last video for this set of notes. Example 4 and 5 are actually going to walk us to where we're going, which is once we know what different types of discontinuities exist and how to find them, then the next question is, how do I check if there is a discontinuity, and then how can I fix it, right? And we said if it's an infinite discontinuity, it can't be fixed. There's nothing I can do that's going to bring those two parts of the graph together to connect. And if there's a jump discontinuity, a non-removable discontinuity, there's nothing I can do to get those two to meet. However, when there's a missing point, when there's a point discontinuity, a removable discontinuity, we can figure out, oh, they're supposed to go towards this destination, so why don't we just find out what that is? So for example 4, we're slowly walking into the definition of continuity, which is going to be the next section. There's a piecewise function. Is this piecewise function continuous at x equals 2? Well, they're nice. They tell us where to look at x equals 2. So we're going to take the limit as x approaches 2 from the left. If x is approaching 2, that means my x's are smaller than 2. That means I'm using this part of the piecewise function. And then I'm going to take the limit as x approaches 2 from the right of 5x minus 7, because this is the formula I would use for x values that are bigger than 2. And I substitute. So I'm going to substitute 2 in here. 2 squared, that's 4, plus another 2, that's 6, minus 3 is 3. So my left-sided limit is 3. Okay? I'm going to substitute this 2 into this function. 5 times 2 is 10. 10 minus 7 is 3. Oh, so what does this tell us? This tells us that the two pieces, by the way, by themselves, x squared plus x minus 3, the top piece, that's a quadratic. It is nice and connected. The bottom piece, 5x minus 7, that's a linear. That's nice and connected. And what we just figured out is they're going towards the same place. So now the only thing I need to check is, what is f of 2? Is there a y value? Does the function tell me how to find the y value at 2? And it does, because of this equal sign. When x equals 2, I'm supposed to use this formula, but we already know that that's going to give us 3. Oh, so then from the left side, it's going towards 3. From the right side, it's going towards 3. And at x equals 2, it is 3. Therefore, this is a continuous function at that particular x value. We only check one point. We only checked at x equals 2, right? But that was what the question was asking. So we're going to say f of x is continuous at x equals 2 because the limit exists, the function value exists, and they are equal. They're the same. I know where my graph is supposed to go. I know that there's a point at that x value, and that point matches where it's supposed to go. So everything gets connected and continuous. This is a common question, usually on the multiple choice test, of confirming the continuity or checking the continuity of a piecewise function. So we'll do example 5, and this will be our last video for this section. Find the value of c that makes the piecewise function q of x continuous at x equals c. Oh, so now at x equals 1, I'm sorry. So now they want us to make the function continuous. Well, how do I make the function continuous? By taking the limit as x approaches 1 from the left side. We're going to use this. And then we're going to take the limit as x approaches 1 from the right side of this. And in order to make it work, they have to be equal. Because if they're not equal, then we're going to get a gap. And I don't want that. I want it to be continuous. I want it to go towards the same place, and I want a y value to exist there. So when I do this, substitute 1 in there, and I'll get negative 2. Substitute a 1 in for wherever you see an x, and you're going to get 1 plus 1c minus 5. Can I just say this is c minus 4? 1 minus 5, that's negative 4, yeah. and then add 4 to the other side. And we found this is the magic value that C in this formula right here needs to be so that my two one-sided limits agree and force this function to be continuous. Because I already know that when x equals 1, I'm going to use this formula, and I already got that it equals negative c. I'm sorry, negative 2, not negative c. That it equals negative 2. And so if I substitute this 2 in over here, if I substitute the 2 wherever I see the c value, that will create the formula that would make everything continuous. So this is now launching into the idea and the definition of continuity, which is we know a function is continuous at a specific point if the left-sided limit and the right-sided limit go towards the same place, and there's a function value, a y value at that point, and that y value is equal to the destination that those two one-sided limits are approaching.